So this workshop is on reinforcement learning that will be hosted by Armin Najarpour Forushani, which has a PhD in biomedical engineering from Polytechnique Montreal, and he's also a great member and mentor of the AI team, and also at ICOMPATO. So Armin, thank you so much for joining us today. We're looking forward to the great workshop you'll give us today on the reinforcement learning, and right after that, we'll catch a break for all the participants. And juste un autre rappel, c'est pour ceux qui veulent écouter la session en français, n'hésitez pas à utiliser l'interprétation au bas de la page où Julie, notre fabuleuse traductrice, pourra vous offrir le service en français. Merci encore, Julie.
Thanks, Monica, for the introduction. I'm going to share my screen. And so you can see my screen, right? Yeah. Okay. So last week we talked about the reinforcement learning. So here I just brought a recap. Reinforcement learning is basically learning to make decisions from interaction with the environment. And we also introduced a return, which is a discounted cumulative reward. And we mathematically show it by GT. We also introduced policy, which is a mapping from states to action. And so the policy, by updating the policy, agent learns to improve the behavior over time. And this learning starts with random action selection. So we also last week introduced state value function and action value function. So the state value function means expected return as specific state with policy pi. And action value function that also named Q function is the actually the expected return as specific state, and with after doing a specific action with policy pi. And also we talk about the optimal policy, which is shown by pi star, and it's the best policy that maximizes action value or state value function, and thus results in the maximizes the return. And this is the block diagram for the reinforcement learning. The agent interacts with the environment, reads from the state from the environment, observation, performs an action, and receives a reward in the next step. So these are what we taught in the last week. But we want to know how to find this optimal policy. So basically, it is an optimization problem. There are two ways. One is to optimize or maximize Q function or state or the action value function, or to maximize the state value function. But here, because of the higher applicability, we use the maximizing the Q function, which and the solution to that is called Q learning. So what is Q learning? It is an iterative algorithm. You see here it has a mathematical expression. This mathematical expression shows how we can update this Q function. This Q function depends on state and action, and also it has other components. This part is reward, this part is learning rate, we have discounted factor. We have introduced all of these details in the last week, but the way to update this Q function is presented here. So this Q function can be represented as a Q table. Let's return back to the previous one. So this Q function depends on state and action. So we have Q table, we have states and action, and for each state and each action, we will have a Q value. So At the start of training, we initialize the Q table, so it can be all the key values can be 0. But over the process of learning, we'll have some values that the Q will not be distributed randomly. So the Q table will be updated based on the training. So we also have concept of exploration and exploitation. So when an agent is in an environment and wants to learn, it updates the policy at each step based on the reward. But at the same time, the agent needs to better interact with the environment. Maybe there are some states that are not explored. So we need to add an additional procedure for the agent in order to better explore the environment. So it's called exploration, which is to increase knowledge by, for example, selecting random action. And also we have exploitation, which is follow the policy based on the current knowledge. And it's important to have exploitation as well as exploration to collect enough information for choosing the best overall decision. Example of exploration and exploitation in the game, in playing a game. For example, when we play the move based on your current knowledge that you think is the best move, it is exploitation. But when you try a new strategy, it is exploration. So this is the basic concept behind it. And during the learning procedure, we need to have a trade-off between these two types of action selection. So something is called epsilon greedy solution exists for making this trade-off. One, with probability epsilon, one can select a random action, which is exploration, and with probability of 1 minus epsilon, it selects a policy-based action. And during the the process of training, which involves episode is when the agent starts from an initial point and follows a number of actions and goes to multiple states for a limited number of iteration that we defined in the code. This is called episode, or it also can be defined when the agent is reached to the target. So the epsilon will be decreased, or we make a procedure for the epsilon to decrease over the episodes. This is the pseudocode for Q learning. This is the way that agent learns. So we first initialize this Q function, or the Q table that I showed in the previous slides, that all the values were 0. And so for a specific number of episodes, we follow a procedure that we initialize the state at a random position, put the agent at random position, and we choose an action based on the state and the Q value. So this is the part that exploration and exploitation happens. This is the action selection part. And when the agent takes an action, it receives a reward in the next step and goes to the next state. So this Q value will be updated. And so this loop will continue until the number of iteration or number of episodes that we specify. You have heard about deep reinforcement learning. So deep reinforcement learning has the same structure as the reinforcement learning. We have reward, environment, state, action, but the only additional part is a neural network that maps the state to the action. So in terms of the Q learning that we taught, we have in the normal Q learning, we have a state, action, and a Q table. But for deep Q learning, we have a neural network that makes this map. So actually, it is the policy inside the neural network architecture, inside the reinforcement learning architecture. And a company called DeepMind has used DeepQ learning to train an agent to play Atari. So this is somehow state of the art. Now let me share with you a code. So I shared a link and I'm going to share my screen. So you can see my screen, right? So Q-learning in GIM. So I tried to find an example with that could match the slides. So it's straightforward and simple example using Q-learning in GIM environment. But these codes are mainly based on the references I provided here, made by Jelena Tostaeva. And please, some part of the code has a render function, and if you this render function doesn't work in Colab, so you can use Jupyter Notebook or just not to run it. It's only used to visualize the environment. And just to recap, when we have no Q-learning, we will have no policy updates, so actions are random. When we have Q-learning, we are going towards optimal policy, and actions will result in the highest reward. And we have the GIM library is made by OpenAI and provides the minimum needed to have an environment, an agent to interact and go step by step. And there is like no need to make simulated environment in many situations. So you can just install the package if you don't have it. It exists on Colab, but if you want to use Jupyter, you should install it. And there are some relevant libraries like NumPy and Matplotlib for visualization. So for this example, we use a simple environment, which is called taxi problem. It already exists in the GIM, so you can just call it and use it. So it's a basic environment. The agent is a taxi, for example, a self-driving car. And the goal is that our agent or taxi moves in the environment to pick up the passenger and drop off to their destination. So let's visualize it. We use this code to visualize our environment. So we import GIM and we can create an environment and just reset the environment because it's randomly generated. And it just shows the environment. So this is the structure of environment. We have R, G, Y, B. These are the location of passengers. The blue means the passenger, and these are the locations of the passenger. The yellow is the taxi itself, and magenta means the destination. And when the taxi is full, the color of this taxi is green. This structure of environment has 6 different actions. So the taxi can move south to the north, east, west, or it can pick up the passenger or drop him off. And each of these actions are shown by a number between 0 to 5. And the states of this problem are 500, and how is it obtained? So we have 25 locations of the taxi. So that if you count the numbers, 5 by 5 places that the taxi can stay, and there are 4 letters for the location of passengers, and also for each passenger we can taxi full or have no passenger in the taxi. So there are 5 different cases. So when you multiply them, you have 500 states. And when you use the codes, the syntaxes from the GIMP library, you can find them automatically using this code. So the action space is 6 and the state space is 500. And to note, an important note about the reward is that the taxi receives a -1 reward for each move. And if it successfully delivers a passenger, it receives +20. And for any illegal move, it receives -10. Let's go to train the model. So this is this is where the Q-learning starts. So we saw the pseudocode of Q-learning. Now we want to see it in the code. So we saw some hyperparameters of the model. So here, later you can just go deeply into the code. Just I try to make it brief, not to explain all the details. So there are some hyperparameters or parameters of the model. And so the first step in Q-learning is to initialize the Q table, which is shown here. And also in order to keep track of reward and epsilons, epsilon is the epsilon that is used in the acceleration and exploitation step. We created 2 lists. And the training procedure starts from this, performs in this for loop. And we have specified a number of episodes. So in each episode, the agent selects an action. So this action can be selected based on the can be selected randomly, which is the exploration, or can be selected based on the current policy. The current policy means to select action when the Q function is maximum. So this is actually the exploitation part, and based on this action, the agent choose a value between 0 to 5 and go to the next state. So the epsilon is selected on random with a value between 0 and 1. And at this step, the agent makes an action. And so based on this action, it receives a reward and goes to a new state. So when the agent receives the reward, the Q function or Q table will be updated, and this is the mathematical expression in code, the one that we presented, that I presented in the slides. So this is the return that which is the total number of rewards, and it shows it's related to the ending of the episode. Something which is important here is that the epsilon for each episode is not the same. We need to increase the probability of having and to selecting an action based on exploitation or based on having the maximum Q function. We need to increase this chance. So it means we need to really decrease the probability of random action selection over the episodes. So this is a mechanism. We use the exponential decay function, and we reduce this epsilon value over the episodes. And then we will have here we keep track of the reward and the epsilon values. Then after this process of training, we can use the visualization library here, Matplotlib, in order to show the rewards that agents receive over the episode. As we see, from negative values, the training total reward has been increased to 0. It means that the agent is learned to get the highest amount of reward. And also we see that we have a decay in epsilon over episodes. So this is a presentation for now about the theory of reinforcement learning and the codes that can implement it in its simplest form. Yeah.
Amazing. Thank you, Armin. Maybe there's some questions from the audience. Est-ce qu'il y a des questions de notre audience? We have one question there, Armin. I'll let you answer.
Yeah, can you explain discount factor? Do we need to update discount? A discount factor means the weight we give to the future rewards, not the reward at the moment. If we look at human, sometimes we don't do something to have something in the long-term future. So if we choose a bigger discount value, it gives more value to the future rewards. And you should check really the research if we need to update the discount value or not. But based on my knowledge, it is a fixed value. How can we interpret the plots at the end? So the more important plot is the reward. So we see that over episodes, the agent learns to collect as much as possible rewards, and at some time after a number of episodes, the reward converges to 0. So because the rewards are negative values, 0 is some like good value or high. It's not really 0 compared to positive. 0 is good. So after a number of episodes, the agent learns how to obtain a maximum amount of reward. And in terms of real application, you need to depends on the application, but you need to translate the meaning of reward into some like real value, something meaningful. But in terms of algorithm, it is maximizing the reward, and we see in the figures that we have reached to the maximum reward.
Okay, perfect. We see another question there from Roshu. What's the average time to train a model?
What's the average time to train the model? It depends on the model. It didn't take that much. It was less than a minute in this case, but if you increase the number of episodes, so the time will increase. Also, some problems are more complicated for the agent to learn. So it takes more time for the agent to explore the environment. It completely depends on the environment and how complicated model you want to use. So Q-learning is not the only method to update or to train an agent with reinforcement learning, but it is one of the most famous and basic ones.
All right, well, thank you so much, Armin, for that awesome workshop. Really appreciate the time and effort put into it.